Hi, my name is Adrian Mroczek, and today I'll be discussing further progress of my project Collision Detection for the Blind. As a brief recap, the previous video outlined changes made to the original project plans. Some of these changes include switching the original microcontroller to an Arduino Nano V3 for better compatibility, adding new components like regulators, battery packs, and additional capacitors, reducing overall weight with the Arduino Nano and other components, while also making schematic improvements. For the rest of this video, I will outline the progress and changes made since then, and also challenges faced and how I overcame them. In my previous presentation, the usage of feedback to warn the user of impeding collisions and also inertial measurement units to account for drift, acceleration, and deceleration were discussed. These components recently arrived after purchase, and progression has been made for their implementation into the project. Soldering was required to interface with these components. I have been able to successfully provide functionality to the components through coding and debugging. The components are working with the other devices, providing desired output and performance. Additional methods have been created providing feedback, warning of impeding collisions like drops and overhangs to the user when certain conditions are met. This was accomplished using if statements, percentage increase and decrease of measured distance, calculations at certain angles. Continued weight reduction was accomplished by breaking off a redundant piece of the MPU's breakout board and also sourcing 2 LiPo batteries, providing 3.7 volts and 900 milliamps per hour each, giving the circuit a total of 7.4 volts and 1800 milliamps per hour when operating in series. These LiPo batteries will also be utilized for the final project. For continued prototyping, a 6 AA cell battery holder operating in series was also sourced to replace the 8 AA cell battery holder operating in parallel in the previous videos. This means the circuit can be provided with 9 volts of power, making the voltage drops a non-issue. The biggest challenge I am facing right now is properly implementing and interfacing the MPU 9250. It has been a struggle to get the code working properly and accurately read the data. So far I have been able to read some data and output it to a serial monitor, but it doesn't seem correct and will need validation. To overcome this challenge, I plan on seeking advice from other students and lecturers with experience using the MPU 2950. I will also research additional libraries available online to incorporate them into my code. Creating feedback with the lidar-lite motor, working in conjunction with the servo motor and lidar-lite, was also a challenge. The initial implementation of my code to the microcontroller found that the code would get stuck looping within the feedback function, causing the servo to stop moving because of the delays used in the feedback method. This was overcome by debugging the code and changing static variables to volatile, because these variables need to be updated during certain calls, and also additional Boolean logic needed to be added. Another unexpected problem faced was the GWS mini servo functioning erratically even when uploading the standard servo sweep Arduino example to the board. This issue was resolved by troubleshooting and debugging the code and the board. The servo regained power and functionality when the microcontroller was powered down, devices were reconnected, and the code was re-uploaded to the board. Recharging batteries is a foreseen issue with the 6-cell battery pack currently used for prototyping. It won't be easy to recharge these cells, so Kern University has provided me with 2 light and rechargeable LiPo cells, which will be operating in series for the finished product. As the project progresses, careful consideration needs to be made for providing feedback of different collision scenarios to the user. I have currently implemented conditions for an impeding drop and overhang, but tweaking will need to be done so that normal environment instances don't set up conditions causing false alarms for the user. Changes have been made to the overall code since the previous video. Additional variables, initialization, Boolean logic, methods, and method calls have been added. A feedback method has been implemented. First, the code will do one cycle, measuring distance, which is then stored in the previous distance variable to be used in the next cycle. During the initial cycle, the feedback method is not called because the initial distance needs to be stored for calculation in the feedback function. During ongoing cycles of the code, the change in distance is calculated as a percentage. If the distance decreases by 40% while the servo position is at an angle between 100 and 160 degrees, the lidar pad vibe motor will vibrate for 2 seconds and turn off. The feedback method will continue to warn the user of the collision until it's avoided. During ongoing cycles of the code, the change in distance is calculated as a percentage. If the distance decreases by 40% while the servo position is at an angle between 100 and 160 degrees, the lidar pad vibe motor will vibrate for 2 seconds and turn off. The feedback method will continue to warn the user of the collision until it's avoided. This slide shows the serial monitor output from the code during operation as discussed in the previous slide. A demo of the devices in operation providing feedback is presented in the next slide. In the coming weeks, full integration and functionality of the MPU 9250 will be implemented. Also, more feedback scenario conditions will be added, and also the 3D case design and printing will begin for the final product.